We'll get started. So we were talking about gradient projection method in the previous class. And the idea inside this particular method is that while taking a gradient descent step, I'm okay to go out of the set as long as I apply what is known as a projection so that I can get back into the set. Okay, so in order to understand this, I want to cover what is known as projection theorem today. So we want to understand this beast called projection. So what is a projection? I have a point Z. Z is in Rn. So the projection of Z onto the set X is argmin X in capital X. So X is a convex set. Z minus X. Okay, so I have a convex set. I have a point Z. I want to find the point X star within this set that's closest to Z in terms of the distance. So I'll make it half of Z minus X square, it doesn't matter. But easier to solve a quadratic optimization problem over a convex set. Okay, yes?
Is this projection different from what we did on the Q conjugation method?
Yes, that it's slightly different.
Slightly.
Yeah, I think let's just keep it at slightly different.
Okay.
The point is that you're picking a different metric over the space
Okay.
through which you are doing the projection. So here we are using the usual Euclidean metric. Okay, this is the L2 norm square. Okay, so the idea is clear. I have a convex set, capital X. I pick a point. Sometimes that point could be inside the set, in which case there is no projection to be done. Sometimes the point is outside the set, at which point of time you need to figure out what's the point X star within the set, capital X, that is closest to the point Z, which is outside the set. Okay, so this is how we define this is how we denote the projection. So Z, square brackets, and then plus sign in the subscript. This is known as projection of Z. Projection of Z onto capital X. Okay, so let's see what this theorem says. The theorem says that for every Z in Rn, there exists a unique X star in capital X. This is only for convex sets, by the way. So don't assume that this statement is true for all possible sets, but it's true for convex sets. There exists a unique X star in capital X such that Z plus equals to X star and Z minus X star transpose X minus X star is less than equal to 0 for all X in capital X. Okay, so there is a unique projection, a unique point, which is a projection of Z onto the set capital X, and then it satisfies this condition. So let's see what this condition says. Z minus X star is this vector. I pick any point X. x minus x star is this vector. So I have two vectors, z minus x star and x minus x star. The inner product is non-positive, so it's less than equal to 0. It can be 0 or it can be strictly negative, but it cannot be non-negative. It cannot be positive. Okay, so what does this mean? It means that the angle between these two vectors is greater than 90 degrees, greater than or equal to 90 degrees. It cannot be less than 90 degrees. Does that make sense? Okay. So no matter which point I pick, I draw a vector, the angle is greater than 90 degree. I draw a vector, the angle is greater than 90 degrees. So no matter which point x I pick, the angle is going to be greater than 90 degrees. Let's look at another example. So I have this quadrant. I have a point z. This would be my x star. I pick an x here, I pick an x here. I pick an x here. So no matter which x I pick, the angle between z minus x star and each of those x minus x star is always equal to 90 degrees in these two cases, or it can be greater than 90 degrees in this case. So that's what projection theorem is saying. Now the next question that we would be interested to understand is, under what conditions on this set capital X is projection easy to compute? So this seems to be an optimization problem, right? So I'm trying to minimize a function of x given the point z. So the question is, under what conditions can you actually solve this particular problem very easily? So let's look into those specific examples. Any questions on this before we move on to that?
Why do you have that second constraint on it?
This is not a constraint. This is just what x star satisfies. So there exists a unique x star that is projection of z onto x, and it satisfies this particular condition.
Is it a theorem or?
It's a theorem, yeah. So let me write it again. So z plus equals to x star if and only if this condition holds. Okay, so the x star is a projection of z if and only if this particular condition holds for all x in capital X. Okay, that's projection theorem. Okay, let's look at some examples. So my capital X is the set of points such that norm of x is less than equal to r. This is the Euclidean norm. This is the 2 norm. Okay, so I have a ball. The question is, what is z plus? So this is a ball. I have a point z. What is the projection x star of this particular point z? Can you guys figure out? So let's say this is the origin. This is 0.
If it is inside the ball?
If it is inside the ball, it's that point is the projection itself. If it is outside the ball, so let's look at. Okay, so let's write it down. So if z is less than equal to r, then it is Z itself. What if Z is greater than R? Norm of Z is greater than R. Yes.
I think it will be through the center and
Yeah.
the connection
Wherever it intersects with the surface. Okay. How do I write it? I think your geometric intuition is right, but I need to write.
Intersection between line and the boundary.
What is that intersection? Yes.
I think it's the unit vector on Z times R.
Right. So what's the unit vector of Z?
Z over norm Z.
Z over norm Z. Perfect. So it's R times Z over norm Z if Z is greater than R. Okay, so is this an easy to compute projection? Okay, so if I give you the R could be whatever, 1000, let's say. Z is a 100-dimensional vector. Is it easy to compute? It's easy to compute. What if it is a 1,000,000-dimensional vector? Even then it's easy to compute. Okay, you can do it in MATLAB. On your simple machine, whatever machine you might have, you should be able to do the projection for, I don't know, 1,000,000-dimensional Z, not a problem. Okay, so easy operation. Let's look at the second set. AX equals to 0. What is the projection in this case? It's not obvious, but you can actually solve it after you spend some time and effort on this. It's given by I minus A transpose A transpose inverse A times Z. Yeah, I'm projecting Z onto this particular subspace. So AX equals to 0, it's a hyperplane passing through origin. So remember, X equals to 0 satisfies this condition. So it's a hyperplane passing through origin, or it could be a line passing through origin. And I have a point Z in the space and I want to project it onto this particular hyperplane. This turns out to be the projection. Easy to compute, hard to compute?
We have inverse.
It's inverse for sure, but it's inverse of a very specific matrix. So if the number of rows, so what is the size of this matrix? Number of rows of A cross number of rows of A. Okay, so if number of rows of A is 50 cross 50, I mean it's 50, then this is a 50 cross 50 matrix, easy to solve. If number of rows in A is 1 million, it becomes difficult to solve. Okay. Let's look at the third set. AX equals to B. This expression is also fairly similar. Again, you can solve it using some complicated techniques, but I'll just write down what the projection looks like. Okay, that would be the projection of Z onto this particular convex set. Box. This is a box constraint, box set. What is the projection? Let me just write it down. So the ith component of the projection is going to be given by this expression. And let me give you the intuition why that is the case. So I have a box. I love drawing boxes. Okay, I have a point Z. What's the closest point in the box? That the closest to Z, so that would be this point, X star. That's the closest point. If I'm here, if this is my point Z, then this is my X star. So the way to figure out what this point is by this particular operation. Difficult, easy? Easy, right? So in fact, on your machine, you can do projection onto a box set even if you have a billion dimensional vector. As long as you have 16 GB of RAM. Okay, the fifth set x greater than equal to 0. What is the projection? It's very similar to this. Zi greater than equal to 0, 0, Zi less than 0. Very easy to do projection. How many of you have done neural network training before? Neural network? No one? Okay, few people. So, once upon a time, long time ago, I was solving some neural network problem and we needed to have a non-negative function. So the way to get a non-negative function from a neural network is to make sure that all the weights are positive or non-negative. So this is the projection operation I had applied, or my student had applied, in order to make sure that the neural network gives you positive, non-negative values at the end. Okay, so that's where we use that particular technique. So very easy to implement even for a complicated neural network. Okay, let's look at the sixth set. X equals to AX less than equal to B. Projection is very difficult. Okay, so projection onto this set is very difficult. Let me tell you why. So AX less than equal to B kind of set is going to look something like this. Right? So it has a lot of corners. Now if you have a point X, point Z, which is outside the set, very difficult to know whether you can, how easy it, it's difficult to know what the projection is going to be. You really have to solve this optimization problem in order to do the projection. So if you look at the current homework, I ask you, in one of the questions, I ask you to project a point onto this set. And what you will notice is you will have to apply some sort of optimization tool in order to be able to compute this projection. Okay, so it's difficult. These are the easy cases. This is the more difficult case. If you have an ellipsoid, difficult. Projection is very difficult. Sphere, projection is very easy. If you have LP norm, projection becomes very difficult. Okay, so depending on the situation, projection is difficult or easy. These are the easy sets that I show you on the board. All the difficult sets are all over the place. Okay.
Check
Any question? Yeah.
if a point is in that set, is it that difficult, or is it also?
No, so these are the easy cases. These are the cases where projection is easy to do. But most of the other convex sets, the projection would be very difficult to do. And the reason why it would be difficult to do is because you have to solve this problem exactly. Okay, this is the problem you want to solve in order to compute the projection. So you will have to solve this problem. Remember, in the previous class, we were talking about conditional gradient method, and we said we have a difficult optimization problem. Let's convert it into a simple optimization problem and solve it, right? So this also turns out to be that case. So you have a complicated optimization problem. You have to do a projection. Now you have to solve a simpler optimization problem in order to solve that complicated optimization problem. Okay, so that concludes our discussion on the projection theorem. Let's go back into the gradient projection method. So what exactly does that method involve? Any questions on this, or can I raise this? Okay. So the gradient projection theorem is that xk plus 1 equals to xk plus alpha k x bar k minus xk. In the conditional gradient method, we had some way to compute x bar k. In this case, my x bar k is in this case, I'll take a gradient step at xk and then project it back onto the set. So this is my xk. This is my negative gradient fxk. This is my point zk, and I'm going to project it onto the set, and this gives me x bar k. And then I'm going to move in this direction. Now, what are the different combinations of sk and alpha k that people use? So we'll talk about that. Okay. So how to pick alpha k and sk? So option 1, sk equals to constant, alpha k equals to limited minimization rule. Okay, so we talked about limited minimization rule in the previous class, so we can just pick alpha k according to the limited minimization rule, and sk could be some constant that works for you. Second is sk equals to constant, alpha k equals to Armijos rule. Remember that alpha k always has to be between 0 and 1. in this algorithm. So even if you're using Armijo's rule, you need to ensure that alpha k is between 0 and 1. If you're using limited minimization rule, you need to ensure that alpha k is between 0 and 1. Okay, so these are the easy ones. Let's look at the third one. Alpha k equals to 1 and sk is picked according to Armijo's rule along the projection arc. What is Armijo's rule along the projection arc? So what does Armijo's rule say? Armijo's rule says is I'm going to pick a big step. If the function change is significant, that's good enough. If it's not significant, I'm going to take a smaller step size and then I'm going to check for that condition, right? That was Armijo's rule. What does Armijo's rule along the projection arc mean? So let me show you by a picture. Okay. So this is my convex set. I'm standing here at xk. By the way, if you are in the interior of the set, it doesn't matter which direction, you can go in all directions. So essentially, all of these methods become gradient descent type methods. So this kind of stuff only works if you are at the boundary of the set. Okay, so I'm at the boundary. This is my negative gradient fxk. And I'm going to pick a big step size. I'm going to project it here. And then I'm going to check if the function value here is much smaller than the function value here. If it is much smaller, then great. Otherwise, I'm going to pick a smaller step size. I'm going to project it back here. And then I'm going to check for that condition. If it violates that condition, I'm going to come back here. I'm going to project here. And then I'm going to check for that condition. Okay, so that's Armijo's rule along the projection arc. So this is the projection arc. This is your projection arc. And I'm moving along the projection arc in order to figure out what's the right step size is for me to pick. And then I'll use that particular step size. Okay, so for this, I need to define x bar k of s as xk minus s gradient fxk projection. S is positive. And then I pick sk to be the s bar beta raised to mk, where mk is the first non-negative integer for which f of xk So this is extremely similar to the Armijo's rule, except that the only difference between Armijo's rule that we studied in the unconstrained problem and the Armijo's rule that we are talking about here is this projection step, because you can no longer step outside of the function, outside of the convex set. You have to do this projection, and then you have to check for Armijo's rule for that particular, like after doing the projection. So this algorithm is good because it gives you a step size selection rule. It's inbuilt within the algorithm itself. You can pick the correct step size for your specific problem. You don't have to fine tune the step size at the beginning. This algorithm is bad because you have to do projection and you have to do function evaluation. Okay. So whenever function evaluation is time consuming, complicated, you cannot really apply this algorithm. So one of the examples that we talked about was when the function evaluation needed collecting data from a lot of different sources. So if you're running some training algorithm on Google's data set or Facebook's data set, it's complicated. Other kind of examples would involve where the function evaluation requires you to run a PDE or solve a differential equation or something like that. So as is the case, if you were, let's say your problem statement was finding the right material for some specific industrial application. So in order to figure out the right material, you might have to run some partial differential equation, some molecular dynamic simulation, in which case the function evaluation would be very difficult and complicated. So you want to use this method when projection is easy and function evaluation is easy. Both of those things have to be right. If both of these are difficult, you do the following. Alpha k equals to constant and sk equals to constant. No headache, no complication, very easy to write code. 2 sentences, the code is over. Have you guys implemented Armijo's rule yet in one of your assignments? Was it part of assignment 2? Yeah. So you have to write a lot of code in order to implement Armijo's rule. This is extremely simple. This one also requires quite a bit of code. This one also requires quite a bit of code. So this one is simple, straightforward, no headache. What's the problem with this? You need to figure out what's the right constant for your specific problem is. And how do you know what the right constant for your specific problem is? Trial and error. You start with alpha k equals to 0.01, sk equals to 0.01, run the algorithm. If it works, great. If it doesn't work, change the step size and try again. If your algorithm is too slow, it means one of these step sizes is very small and you need to increase the step size. If your algorithm is moving around a lot, if you're adding a lot of noise, it means that your step sizes are too large and you need to reduce the step size. Okay. Wonderful. Any questions so far? Okay, no questions. Awesome. So this completes another method, gradient projection method, for solving optimization problems over a convex set. We'll move on to the next method, which is the Newton's method. So what is the Newton's method equivalent for optimization over convex sets? Okay, so let's talk about that. constrained Newton's method. So in the unconstrained case, what was Newton's method? Dk was second derivative of xk inverse gradient fxk. Oh, with a negative sign, right? Yeah, negative sign. That was my Newton's method. I picked the second derivative of the function. It's a symmetric matrix. Hopefully it is a positive definite matrix. If it's a positive definite matrix, you take the inverse, multiply it by the gradient, put a negative sign, that's your descent direction. And what did we notice about the Newton's method? It's extremely fast. We've run it in simulations, you've seen how quickly Newton's method converges. Some of you in your assignment have noted that within 2 or 3 step Newton's method converges, so I can't really compute the error. The right way to compute the error is you start from very far away. So then you can actually see how quickly the error is going to 0. Okay, so how do we come up with a constrained version of the Newton's method? Okay, so one of the things that we discussed in the unconstrained case, and I want to recall that discussion again, how did we compute this dk? So there are multiple ways to think about Newton's method, but one way to think about Newton's method is I let my dk to be the argmin of d in Rn fxk plus gradient of fxk transpose d plus half d transpose second derivative d. So this is a constant. This is the first derivative. This is the second derivative. This is the Taylor expansion series approximation of f of xk plus t, right? So I have the original function. It's a complicated function. It has ups and downs all over the place. What I'm going to do is do a second order Taylor series expansion of the function around xk and find the descent direction d by minimizing the second order Taylor series expansion of the function around xk. Okay, and that gives me, that's exactly equal to this expression. So with this in mind, what should the constrained Newton's method do? So now I'm no longer in Rn. Okay, I cannot go anywhere in Rn. I need to be able to stay within the constraint set. Okay, so what I would do is I will pick my x bar k equals to argmin x in capital X So I take the second order Taylor expansion around xk, but I'm restricting myself to points within the set itself. Like, let me draw a picture to make it clear. So I have this convex set I'm standing here at xk. Earlier, what I was doing was looking at the descent, looking at the gradient, negative gradient direction, and I was descending along that particular direction through some sort of projection. Now, what I'm going to do is approximate the function at this point, but I'm not approximating on this side of the space. I'm only approximating on this side of the space because that's part of the constraint set. So, what's the Taylor series expansion inside the set? Well, my x is in capital X. I'm looking at all the directions x minus xk such that x is in capital X. So I have a point x here. It's in the capital X set. And I'm looking at all the directions x minus xk and then minimizing the second order Taylor series. The only difference between this algorithm and this algorithm is this term sk that appears in the denominator, which is the step size. So same as the step size we were talking about in the previous algorithm. So you just make sure that you pick an appropriate sk. So typically it will be 1, but you can pick some other value in order to either make this term negligible. So you pick a very high value of sk, then this term is negligible. You pick a small value of sk, then this term is prominent. So that's Newton's method. Okay. Any question on this? If I were to put this number here, if I were to put this s here, what I would get is minus s times the second derivative inverse times the gradient. So it doesn't matter. In this case, it didn't matter because you are going to multiply this by alpha anyways, so it didn't matter alpha times s. In this case, it sometimes matter because x bar k, you are essentially picking an x bar k and then you are trying to descend in this particular direction. So that's where this sk terms becomes useful. So that's my constrained Newton's method. And if you want to make it approximate Newton's method, just substitute this second derivative with some approximation of the second derivative term.
Why in the second? The steps as escape term doesn't appear in the first one.
In the first one, so this one?
No, that one.
This one?
The one, the objective function of the optimization. Yeah. But there are two terms.
Yes, there are two terms.
And the sk only appears in the second term.
That's right. Yeah. So what's the question? You want it to appear in the first term as well?
Why it doesn't appear in the first term as well?
It doesn't matter. You just need to scale up one of the components. So you have two functions. Let's say you have function f1 plus lambda times f2. If you want to optimize f2, you pick lambda to be very high. Okay, then f1 becomes very small in comparison to f2, and therefore you are optimizing f2. If your lambda is close to 0, you're pretty much optimizing f1, and f2 is just a small perturbation to f1. And when lambda equals to 1, then you are kind of picking the right balance between f1 and f2. So that's pretty much what you are doing. So if you have lambda 1 f1 plus lambda 2 f2, you can as well write it as lambda 1 times f1 plus lambda 2 over lambda 1 f2. And this term is not participating in the optimization. I mean, it changes the value, but it doesn't change the argument. And what you care about is the argument. What I care about here is the argument, not the minimum value. Any other question? Yes.
Does this sk affect those whole terms?
So sk is basically how much do you value the second derivative term. Okay. So if sk is very large, then you don't value the second derivative term because sk is appearing in the denominator. So if sk is large, then this term is basically going away.
You still have whole terms behind the second order.
Yeah, you ignore all the third order and fourth order terms here.
Yeah,
Okay.
sk is not going to affect anything.
sk is not going to affect any of that. Yeah. Yeah. I mean, look, if you're doing all the third order and fourth order term, you are complicating the descent direction, right? You might get a faster algorithm if you pick a third order derivative as well. But then the question is, you want to make sure that this computation is easier. Okay. So we only go up to the second derivative because third derivative and further derivatives make things far more complicated. And so remember, you have to compute decay at every point of time, and then you have to do a descent, and then you have to recompute everything all over again. So you want to maintain a balance between the computational complexity of one step versus the number of steps you need to take in the algorithm.
We have a Taylor series approximation, and that Taylor series approximation is kind of what I'm talking about, general functions in the neighborhood, right?
That's right.
Okay, so why wouldn't we have a wall constraint where x isn't quadratic x, but also x should be in wall close to xk?
So you are approximating the function around xk. So you have the function f of x, this is x, this is my function, and I am doing the approximation. This is my xk. I'm doing this. This is the second order Taylor expansion of the function around xk. And this is the point where your next, the optimal solution that you get is by minimizing this function. This is what your decay is, right? And then you take a descent, you take a step in this particular direction, you reach here, and then you do the second order approximation of the function at this point.
The second order Taylor series approximation is correct, or is that very close? Does a good job of approximating if the d is kind of small?
Right.
So why wouldn't we have? Why we are not constraining d to be small here in this problem?
Good point. So the question is, why aren't we asking d to be small? So remember that alpha k controls how far you want to descend, right? So you have two parameters here, alpha k and sk. So sk controls how much weightage you want to give to the second order term, and alpha k controls how far you want to go in that particular direction. Okay. Any other question? Okay. Awesome. So we covered two algorithms today. One was gradient projection algorithm. The second one was constraint Newton's method. One of the things we mentioned about the gradient projection algorithm is that the projection step has to be simple and straightforward, easy to solve. Even going back one more class, we talked about conditional gradient method. In conditional gradient method, again, you had to solve a linear objective function over a convex set. Okay, so there is a special class of convex sets that are very difficult to solve. So let's talk about, and we'll be talking about it in the next class, but I want to introduce that method right now. So that's called manifold suboptimization method. And what is the idea there? I'll just introduce the idea and then we can disperse, and we'll come back again on Friday and we'll talk about it.
The project onto those sets are difficult, or?
Yeah, so the sets, the class of sets that I'm trying to talk about is, I want to minimize f of x such that ax is less than equal to b. Okay, so in condition, so if this is the convex set ax less than equal to b, remember ax less than equal to b is, let me just draw a convex set where ax is less than equal to b. I'm going to draw a house. This is AX less than equal to B type of set. Okay. So this is so there are multiple surfaces. There is one surface which is this surface, one surface which is this surface, there is one here, and then there are three in the back. Okay, so there are six surfaces, six hyperplanes, and your set is contained within those six hyperplanes. Okay, another kind of set would be something like this, going all the way to infinity, and everything inside is part of your constraint set. So these kind of sets are denoted by AX less than equal to B. It's extremely hard to project a point onto sets of this type. It's very difficult to solve an optimization problem over sets of this type. Okay, so now we need to come up with an algorithm. So for sets on which projection is easy, we'll use gradient projection method. For sets over which linear optimization is easy, we'll use conditional gradient method. Now, I've encountered a set over which both of those operations are difficult. I need to do an optimization over this class of convex set. So what would you do in this situation? So let's go back to 1920s, 1930s. Okay, so World War II is going on, and the president of the United States comes to you and says, look, we need to move the troops, we need to move supplies, we need to move ammunitions all across the Europe. There are so many people fighting here, so many people fighting there. We need to send them water, we need to send them food. You write the optimization problem. You want to minimize the total cost of moving supplies from, I don't know, somewhere in the United States to somewhere in Europe at different fronts. And there is a whole bunch of constraints, like what's the total amount of water you need in Europe, whatever, country one in Europe versus country two in Europe versus whatever, all the places. Okay, so you have written down a whole bunch of constraints, and this is the problem that appeared. So there is X is, let's say, 100 dimensional, and AX less than equal to B is like 1,000 dimensional. There are 1,000 such constraints. So you are in this, you're trying to optimize a problem over this particular set, and you have 1,000 different hyperplanes that are enclosing that set. And now you want to solve that problem.
Is F convex?
Sorry?
F convex.
Let's assume it's convex. Let's assume it's linear. Okay, so just pick the simplest continuous function, convex function, which is C transpose X. But this is the constraint set, and the reason why I'm talking about 1930s is because this problem was actually solved in 1930s for exactly this reason. You know, we wanted to optimize the movement of troops, and somebody posed this as an optimization problem at that point of time, and they came up with the algorithm to solve this problem. Okay. So I'm going to leave you on this cliffhanger until Friday, and then on Friday, I'm going to give you what the algorithm is. But think about it. This is a problem you have to solve. Think about how you would go around solving this problem. Thank you so much. Thank you.